Here I'm going to solve a system of differential equations, linear differential equations. This is a 2 by 2 system, so presented in this form you can see that x prime is equal to 2x plus 3y and y prime is equal to 2x plus 1y. First we solve the characteristic equation that was given in my last video, or one of the last two videos. So the characteristic equation, we'll take that matrix A, the 2 by 2A, subtract lambda times I. So what happens is we'll just be subtracting lambda, a constant, a scalar, down the main diagonal. And these bars represent the determinant, so I'll find the determinant of that, AD minus BC, so the product of the main diagonal minus the opposite diagonal. That gives me an equation here. This is a polynomial equation, and it will be a quadratic equation. So by expanding that, combining like terms, and then factoring, I see that I have two solutions to the quadratic equation. Lambda will be equal to 4 and lambda will be equal to -1. Those are my two eigenvalues. Once I have an eigenvalue, then I will solve the equation. This was A minus that eigenvalue all times. So this should be I actually. So a matrix minus lambda I all times V is equal to 0, and I'm going to solve that for the eigenvector v1. So I apologize. This is the equation presented before that we'll be solving to find our eigenvalue vector 1. Taking A and subtracting lambda, so for lambda equals 4, I subtracted lambda down the main diagonal. You'll have 2 minus 4 would give you -2, 1 minus 4 gives you -3. I'm multiplying this by a vector v1. You can put in any letters here. I think your book uses k1 and k2. Sometimes a book will use x's or v1 and v2. But you want to solve for a vector such that this product is true. When I multiply the first row out, I have that -2k1 plus 3k2 is equal to 0. That's denoted here. If I had done that with the second line, you'll notice that that is just a multiple, a constant multiple of this by -1. So that will give me 2k1 minus k2 equals 0. Well, fundamentally those are the same. They're constant multiples of each other. So we break this down a bit. This is the same thing as saying 3k2 equals 2k1, you'll notice. And I could solve for k1 or I could solve for k2. This is the part that is going to get confusing, and I wish that we were in class so I could work with each of you. This is where you're going to have questions. Please contact me when they come up. V1 can be anything, but it has to represent that relationship. This is not the only V1 possible, but what I've done here is for V1, I've just chosen to plug in for K1 1. If K1 is 1, or actually I plugged in K1 equals 3, I'm sorry about that. If I let K1 equal 3, 3 times 2 is 6, that forces K2 to equal 2. So in this case, I've typed up V1 equals 3, 2. That's not the only way to do it. I could have let K1 equal 1, in which case K2 would have been 2/3. If this were 1, that would have been 2/3. Well, if you're thinking about a vector, so go back to your Cal 3, and if you're in Cal 3, the beginning of Cal 3, you still looked at this. If I am comparing the vector 3, 2 to the vector 1, 2/3, those are parallel vectors, they're constant multiples of each other. In differential equations, when I talked about a spanning set, we don't care about the magnitude of that vector right now, we just need it to span the same direction. And so we just need those vectors to be parallel. What I'm getting at, the back of the book may have completely different answers from what you get, but that doesn't mean you're wrong in this section. This vector, I just need a parallel vector. So if you get a vector and you decide that, well, I think that this K1 should be 5, and 2 times 5 is 10, so K2 will be 10/3. That's not wrong. A little strange, but not wrong. So remember that there are multiple ways to do that. X1 then, so our fundamental set will contain the solution x1 equals c1, a constant multiple of e to the lambda t. We used lambda equal 4 here and got the eigenvalue 3, 2. This will be one of our fundamental solutions. We'll now find our second fundamental set by letting the eigenvalue equal -1. So for lambda equals -1, we again solve this, and again you'll notice that I probably copied and pasted. I need that matrix in there in order for that to make sense. So I need to solve this equation. I have already substituted lambda equals -1 in the characteristic equation, or down the diagonal. I've subtracted that. So 2 minus -1 gives me 3, 1 minus -1 gives me 2. Solving this equation, we have 3k1 plus 3k2 equals 0, or we could have said 2k1 plus 2k2 equals 0. Those are exact same statement. Both are saying that k2 is equal to -k1. To keep this easy, I've substituted 1 for k1, and that forces k2 to be -1. You could have, of course, had -1, comma 1. You could have had 5, comma -5. Those are parallel vectors. Both span the exact same ray in the, or exact same line, really, in the two-dimensional plane, the Cartesian plane, and so both would work for this. Remember that C2 can be any constant multiple, and so that's what makes that work, where you can have different vectors, because C2 is a constant that could change the magnitude of that vector by any scalar. So this is what we have for our second part of our fundamental set, and that leaves us with a general solution of this form. You'll notice that right now you'll have constant multiples. This is very similar to what we did in chapter 4. This is saying that x of t is equal to c1 3e to the 4t plus c2 e to the -t. And it's saying that y of t is equal to 2c1 e to the 4t minus c2 e to the -t. So you're getting two different solutions there. If you're thinking about it, it's in vector form. Alright, that is our first example. You could pause the video, maybe work back through that, or maybe work through the first homework problem. In the next video, I'm going to talk about the tendency of solutions, and then we're going to work another type of case. So before I jump to the next type of case, the tendency of solutions. So what we had noticed that was a 2x2 system, so we had two different members of our fundamental set. Each of those had this form, but one of the lambda values was positive and one was negative, so I want to discuss that. We did talk about this a little bit in chapter 4. I kind of discussed this. I was trying to do systems since I knew that we might be rushed for time towards the end of the semester, so I tried to introduce it a little early. For our solution set, earlier we had a general solution of this form. So for lambda equals 4, this portion, what will happen is we're going to span the vector 3, 2 as, so remember that 0, 0 was an equilibrium solution. As the values for t go to infinity, this is going to explode, this term right here. So what this is saying is the absolute value of that, as t grows to infinity, this term is also, this term right here without the constant, is going to grow to infinity, unbounded. And so we call that an unstable solution there. The case where this is going to tend, what I mean by unstable, these solutions will tend away from the equilibrium point. You'll remember in chapter 1 I talked about phase diagrams, and I gave you some phase diagrams for two-dimensional plots. For this, along the ray 3, 2, or along the vector 3, 2, the solutions are going to tend away from the equilibrium 0, 0. For this portion, along the vector 1, -1, solutions will tend towards the equilibrium, because as t grows, this exponential decay right here, those values together will grow smaller as t gets larger, and so these will go towards the equilibrium 0, 0. We call that a stable solution. So, and for eigenvalues equal to 0, I didn't give you one of those right now, but those are kind of those are the boring cases. But here we have unstable or stable. So I want to talk about this. For real distinct eigenvalues, we have 3 cases. If one of your eigenvalues is positive and one is negative, this is what I'm saying for our last example actually. So for one of those, when the eigenvalue is -1, solutions tend towards. So this picture doesn't represent our exact last case, but imagine this was the vector 1, -1. It's not too unsimilar. And along that vector, because the eigenvalue was -1, then the solutions are tending towards 0, 0. Now pretend that this was our other eigenvector, which was 3, 2. And you could pretend that that was 3, 2. That doesn't look too unlike 3, 2. You'd go out 3 and up 2, out 3, up 2. So because constant multiples, we can go in the positive or negative direction. That's why we span that entire line there in the Cartesian plane. And because the eigenvalue there was 4, as t goes to infinity, then we're sending solutions away from the equilibrium. So that tells us that our solutions, they're kind of bound between, you can think of these as asymptotes, and our solutions are bounded between those rays, those vectors. So following this drive, so you can think the slope field, solutions are going to tend, because of the movement towards the equilibrium here and away from this, then those are why those curves tend in these directions, and like so here and here. What those different curves are representing are different possible solution curves for different values of C1 and C2. And so that gives us all of our possible solution graphs of our solutions. This is called a saddle. So if one of your eigenvalues is less than 0 and one is greater than 0, we call that a saddle point. So the the equilibrium point when one eigenvalue is positive and one is negative, then we call that equilibrium point a saddle. In the case where both of your eigenvalues are negative, then we call the equilibrium point, which was 0, 0 in our case, a sink. In this case, you might have solutions that do something like this. So both of your eigenvectors, both of your eigenvalues are negative, and so along those eigenvectors, solutions are tending towards the equilibrium point. So we call that a sink, like a sink drain. All the solution sets are tending towards 0, 0. And if both of your eigenvalues are greater than 0, we call that equilibrium point a source. So solutions are tending away from the equilibrium point in this. This would be like the faucet on a sink, the water coming out, so the source. Alright, and now I'm going to do another case. In the case where you have repeated eigenvalues, so I'm going to discuss this. If you have repeated eigenvalues, remember that we have to have linearly independent eigenvectors, again, to span the 2D plane. You can't have repeated vectors. You won't have a spanning set that covers the entire 2D plane. Because those constants can be different values, we want to be able to find all those possible curves. And so you need linearly independent eigenvectors. In this case, so there are kind of two subcases here. If you can find linearly independent eigenvectors from solving your system, then that makes it a piece of cake. If you're able to do that, then it's not really a big deal. If you're not able to do that, then our solution set will have this form. So this is the harder set. If it is only possible to find one eigenvector, then what you'll have to do is solve a new equation. So you'll take the eigenvector you already had and solve for a second eigenvector, and your solution set will have this form. I would write this down. I'm going to use this for an example right now. So what I'm doing right now, I realize the videos are long this week. It's been tough to condense this. I'm not doing the kind of easier case. I recommend reading the one in the book or just practicing the first example I talked about, because those are kind of straightforward. But if you have repeated eigenvalues and you cannot find a second eigenvector, that's what I'm about to work. Those are kind of the harder case. So for this case, I'm going to solve this system as given here. You might take a minute and write that in matrix form. Write that as a matrix equation first. After you've done that, I'm going to go ahead and solve for the eigenvalues. So once you wrote this as a matrix equation, I have taken the determinant of A minus lambda I, and so I've subtracted lambda down the diagonal. By finding the determinant, I'm given a quadratic polynomial. I expanded that, combined like terms, and factored. This tells me that I will have one eigenvalue. It's a repeated eigenvalue. This was a 2 by 2 system, so I still must have 2 independent eigenvectors. I first work just as I would have in the first example. I subtract the lambda, so plug in 2 down the main diagonal. I multiply that through. You'll notice that from both of those lines you would have gotten this relationship. They're multiples of each other. That's bad news. If they were not multiples of each other, if you had a 4 and a 2 here, that's good news. That immediately gives you 2 different eigenvectors. You would have set those up. Your first eigenvector would have come from the first relationship, your second from the second. So that's why I'm not doing that case. I feel like you guys can hopefully figure that case out. The problem here that makes this kind of unhappy news is that these are multiples of each other. So it only gives us 1 eigenvector right away. Since k1 must equal k2, you can use 1, 1, you could use pi, pi, you could use 4, 4, whatever you choose. For the second eigenvector, we must solve this equation. Now I just noticed, because I'm doing this in live time, I used v1 and v2 earlier, and then in this slide I used p. I think your book might use p, and so that may be why I typed this up like this, but v represents the eigenvector you already found. This would be the second eigenvector you need to find. We're only using this for when we have repeated eigenvectors, and when we have repeated eigenvalues, and you need a separate eigenvector, a distinct eigenvector from the first. So what we will do is I have substituted 1, 1. We found v was 1, 1 earlier, so this just comes straight from the last slide. And I'm going to substitute that in here to try to find a second eigenvector. So here I'm using p1, p2 for p. This is my v, 1, 1. From the first or the second line, they're multiples of each other, I have that p1 minus p2 equals 1. Again, you could plug any numbers in for p1 and p2. I have let p1 be 2 and let p1 equal 2 and let p2 equal 1. Again, you could have used other numbers. You could have had 3, 2, 6, 5. As long as those are parallel to this, and what I mean, as long as those have that same relationship, those wouldn't have necessarily been parallel. But what I'm saying there is, as long as whatever your value for P1 is, as long as your difference between those values would be 1, you can have many different vectors here. Your C1 takes care of those constant changes. Our general solution then would have the form x is equal to a constant multiple of v1 times e to the 2t, and because we had 2 different eigenvectors, then you have to have this set up. So you'll notice the first one, we take what we had and multiplied by t, and sometimes you'll see this e multiplied out front because it appears in both. So you'll take the first eigenvector and multiply by t, and then you'll have the second eigenvector that you received. So this would be how we'd express our solution set. Now if you have initial values, then next what we'll do is substitute those values. So because this was x of 0 equals 2 and y of 0 equals 1, then that is the same thing as saying capital X of 0, because that's a vector representing x of 0 and y of 0. So I have that over here, 2, 1. And what I've done for this middle part is substitute t equals 0. So here I have just 1, 1 times c1. For this, because t is equal to 0, it cancels completely. And here I'll have c2 times the vector 2, 1. I need to solve this. It's just an algebraic system. When I solve this, I think I used elimination by addition, and I have that c1 is equal to 0 and c2 equals 1. I can substitute those back in so that I have a solution of this form. So by letting c1 equal 0, this completely cancels. c2 is 1, so you'll see all I really have is this portion in the brackets. So that is an example for when you have repeated eigenvalues and you need 2 distinct eigenvectors. In the next video, I'm going to go ahead and stop this video because I'm afraid it's too long. In the next video, I'm going to discuss how to deal with complex eigenvalues.